First of all, I want to thank the organizer for this kind invitation. It is my pleasure to explain our works on Boolean mechanics in decoherence and the classical limit of Boolean mechanics with this audience. Okay, I want to acknowledge some people who is working with me, Damiano Mario, Enrique Colomés, Guillem Alvareda, also Albert Banseny and David Tena with this work of the quantum to classical transition, and also Travis Norson, who discussed a lot with him about the motion of the conditional wave function, also some financial support. Okay, basically I want to introduce my talk by discussing a little about what is the decoherence, or at least what I understand by decoherence. And the first question is, it seems that most of the people think that just decoherence is just the problem that we have because most of the systems are not isolated and they have some environment and there's some interaction with the environment that you don't know exactly how to treat, and this is what we call decoherence. There are several ways to mathematically treat this entanglement between the environment and the system. One is trying to eliminate the non-diagonal elements of the reduced density matrix, also trying to understand the environment as some kind of thing that is monitoring the system, and because it's monitoring, it's producing some dynamics in the system. Also, there is the environment-induced superselection that says that the interaction between the environment and the system provides some states that are more robust against fluctuations than others in the system, and this is the ones that survive decoherence. But there is also some way of understanding decoherence for closed system, unless there are very simple expressions for how to arrive to a classical system in some textbooks that say, okay, just put the Planck constant equal to 0. It means that there are some magnitudes that compared with the Planck constant are small or are high. In these limits, basically you arrive to a classical limit. You don't discuss nothing about the environment. You can also say that there is a large number of particles. Or you can say the Ehrenfest theorem that says that provides you some classical limit without discussing the environment. And there is also another question: is that if the coherence is something technical from the theory that you have to work mathematically to develop, or something that is ontological in the theory. In fact, there are theories that answer this question positively and say that, okay, the coherence is something that you have to, some postulate that you have to put in your theory, like GRW, that says that the evolution of the system has some intrinsic spontaneous collapse that is providing some decoherence in your system, but it's something not some technicality of the environment with the system, is something intrinsic to the theory. So somehow the coherence is a little fuzzy concept. And for all practical purposes, how we model the coherence in the systems, basically we work more or less in this way. It says, okay, let us work with the reduced density matrix of some part of a larger system, and we have some evolution, that is the evolution with the Hamiltonian of our system, and we put everything that we don't know and that we call somehow the coherence in another superoperator that makes some evolution to this density matrix. Okay, this because we have some problems to understand exactly what is this term that we have to put. You have to put more or less phenomenologically, and you can somehow introduce the quantum to classical transition just in this term. You can introduce dissipation. You can introduce irreversibility. You can put a lot of things just in this superoperator. Okay, so for all practical purposes, when you deal with the coherence and you have the many-body problem that says that you cannot solve this directly, all quantum theories become somehow universal, because if your experiment is not fitting exactly with your theory, okay, it doesn't matter. You just improve a little your decoherence operator or whatever you call until you fit correctly your results. This idea is not bad. It's good if you are quantum engineering. Means that, okay, so in my modeling, I am able to put dissipation and irreversibility, and I am able to make my predictions quite close to what I get in a laboratory. But from a fundamental point of view, obviously this is somehow an ugly result, because somehow you have to eliminate all this stuff about the coherence, try to test if the quantum theories are universal or not. I mean that if you try to provide a different theory that has some limited quantum locality, but in all your experiments you are able to argue that the coherence provides you some difference, then it's quite difficult to arrive to some conclusion. Okay, so this is the introduction. In my talk, I will basically discuss two topics, all within Boolean mechanics. And one will be introducing dissipation in the Boolean mechanics using this concept of decoherence. Not exactly this concept of decoherence, but something very similar. It says that, as Travis show later, there is this concept of the conditional wave function, where you have some room to put some new physics in the problem, and you are able to put something inside. And then I will, the most important part of my talk will be this second part, that I will avoid completely the decoherence, and I will try to study the classical transition just from pure Boolean mechanics, without imposing nothing else than just the basic laws of Boolean mechanics. Okay, let us start by the first point. The first point, I will explain a little what is the Boolean conditional wave function. I will explain again. And I will basically discuss one particular way of putting decoherence is just the electron phonon dissipation with this approach. Okay, let me introduce briefly what is Boolean mechanics. Travis has already done, but I will do it quite rapidly. Okay, orthodox quantum theory tells you that an object cannot be a wave and a particle, and there is other people that say, okay, one object no, but two objects can, especially if you deal with one wave and one particle. So basically, Boolean mechanics is just this, is just an explanation of quantum phenomena that needs some wave and needs some particles. The wave is exactly the wave of the Schrödinger equation that you have. You can write it in a polar way or in a complex way as you want. And these are the particles, that the particles are guided by this wave function solution of the Schrödinger equation. And because of these trajectories are guided by this wave function, you exactly reproduce most of the problems, or most of the results that you get with orthodox quantum mechanics. This is non-local because the wave function is non-local. This is contextual because if you modify your experiment, modify the wave function, these trajectories are modified because you modify the wave function. And also is unpredictable at the laboratory level. It means that in the laboratory, you are not able to know what is the result of your experiment. Although the theory, from an ontological point of view, is deterministic. It means that if I was able to know this position and this wave function, I will perfectly know what is the evolution of my system. But this is impossible, because if I want to know the position of these particles, what I have to do is measure the position. For example, I put a screen, and I go, okay, the particle is here. But then I break completely the wave function. I break completely the wave function of my system. So I have to choose. Do you want the wave function or do you want the particles? What do you want to know? But you cannot know both. So from a practical point of view, Boolean mechanics is also random. But from an ontological point of view, it's just a deterministic theory. Okay, let us explain the conditional wave function. This is a problem. This is the many-body problem. Everybody knows this problem. This equation is linear, non-unitary, and lives in the high configuration space. But you can do this. If you play with these trajectories, if you play with Boolean mechanics with these trajectories, you can do this. You can do this. Instead of working with this wave function that lives in all this degree of freedom, you can use with this wave function just put in here a number, another number, and just leave this as a degree of freedom. So basically, you have a wave function that lives in a real space. And this is what we call the conditional wave function. Okay, and you can also ask, what is the equation of this conditional wave function? And this is the equation of this conditional wave function. This is just something no, this is the kinetic energy, this is the potential, and these some additional potentials. And these additional potentials, at this level, you are unable to know exactly what, if you are just looking at this part from here, you are not able to know what is their shape. To know their shape, you have to know all the systems. So somehow you have some feedback, and you are unable to further evolve. But you can make some approximations for these terms according to some physical input that you have from the behavior of this. And this is what we do. Okay, we have this equation. Instead of working with this equation, we work with this equation. And in this equation, we want to make our goal is just making some phonon interaction between our electron and a phonon that makes some scattering mechanism. And basically, what we can use is just making this wave function, that basically is this wave function, that this part corresponds to this part, and this part corresponds to this part. And because of this shape is basically, this is just a step function is 0, and the time t1 is equal to 1. So you are making some kind of change of the momentum, and this is when you have some evolution with the phonon. Okay, and basically here I show you some picture. This picture is the normal evolution of the Schrödinger equation, and this picture is the evolution of this system when at this time I have some collision with a phonon, and with this collision with a phonon, I change the momentum of my electron, and I change from a non-resonant electron to a one that is resonant because I have changed the momentum, I have changed the energy. Okay, I want just to show you that with this this is the current that you measure in the laboratory as a function of the bias that you put for some typical device. This is a resonant tunneling device. This is without the scattering. This is with the scattering, and you approach more closely the experimental results. Okay, and this is what I wanted to discuss. This is what I have to discuss, that with Boolean mechanics, you are able to put this with the conditional wave function because you have some additional degrees of freedom, some additional potentials to treat interaction with the environment. You are able to put all this kind of physics, and this is very nice from a quantum engineering because they can approach very closely all experimental results. You can put whatever you want, you can put it in your equation in these terms that I explained to you. But I changed completely, and now I forget about the coherence, and I want to explain the quantum to classical transistor without invoking the coherence, without saying nothing about the coherence, just from the Boolean mechanics. Okay, I will start with a frustrating single particle Boolean attempt. And okay, firstly, let me mention what is the similarities between Boolean mechanics and classical mechanics. Both deal with particles, so this is very nice. So both theories deals with particles, so it seems that they are quite close. Both are able to deal with single experiments. They don't. Normally in quantum mechanics, you deal with ensemble of experiments. No, this is a single experiment. Then you can make an ensemble by repeating your single experiment many times. But in principle, you deal with a single experiment. And both have no measurement postulate. In classical mechanics, when you measure, you make some interaction with your system. And in Boolean mechanics, when you measure, you make some interaction with your apparatus. This is exactly the same. Okay, so this is some idea of Rosen in 1964 that says, okay, let us write this Schrödinger equation. This is the Schrödinger equation for a single particle. Let us write this equation by putting here inside the polar form, the modulus, and the phase. And from this complex equation, I arrived to two real equations. One is the continuity equation, and another is the quantum Hamilton-Jacobi equation. And if you look at this is not typical from classical mechanics, but there is a way of understanding classical mechanics with what is called Hamilton-Jacobi equation. It's just exactly this, but without this term. So it's obvious when you arrive to a classical system. You arrive to a classical system when you are able to put this equal to 0. But if you try to study this problem carefully, you arrive at is a very ugly solution. And I explain why it's not a good solution. Because in each point of the space, I want to satisfy this equation, and also this equation. But in each point of the space, I have only 2 degrees of freedom. I can choose what is my modulus of the wave function at this point, and what is the phase of the phase of the wave function at this point. So basically, this system has no solution. And for most of the potentials that I can imagine, there is no solution. There is no way to satisfy all these equations with a wave function. So it seems that although Boolean mechanics has a lot of similarities, it seems that it has some problems. Okay, let us see what is the problem. The problem somehow is that we deal with a single particle problem, and this is something very, very strange. Classical mechanics is nothing about a single particle, quantum particle. A quantum particle will never be classical, or it will be very difficult to be classical. Why don't we deal with a many-body problem? Okay, let us try to, instead of working with one particle, let's try with an apple that has a lot of particles in the apple. So we start from this many-body Schrödinger equation. But even if we change from single particle to a many-body problem, it seems very difficult that one of the electrons of the apple will be classical. Because this electron in the apple, although it seems classical, I'm sure is interacting with the rest of the atoms to be some kind of molecular, whatever, and this is a pure quantum effect. So it's difficult that one electron will behave classically. So let us make another assumption. Let us try to make classical not the electrons of the degrees of freedom, but just the center of mass of this problem, just the center of mass of the problem of a many-body. Okay, so I change the variables. I put this this equation, and I use also this equation. This is very strange, but it's just to have a nice equation here. The important thing is just this one, the trivial center of mass. This is just to avoid some terms here that I will not care, because I will not care about this. I will only care about this degree of freedom. Yeah? So this is the equation that corresponds to this equation when I make this change of variables. And now I can make also the same that I do. I can make put the polar form of this wave function, and this is the quantum Hamilton-Jacobi equation. And you see that you have this term that is the phase, the potential. You have the kinetic energy of the center of mass that has a different mass that is much more larger than the mass of the rest of the degrees of freedom. This is the quantum potential associated with the center of mass, and this is the kinetic energy with a lower mass, and the quantum potential also with a lower mass. Okay, I can compute the velocity of all the particles and the velocity of the center of mass that can be related with this. And also I can make the time derivative of this. If I make a time derivative of this, I arrive to this equation. This is quite normal. This is what I get previously for the single particle. But now this is a many particle. Well, it's a single particle equation for the center of mass, but it depends on all the rest of the particles in this way, because this modulus depends on all the particles. Okay, so what I have to do to arrive to a classical system is just to be able to be sure that this term is much larger than the other terms. Yeah? And it can be shown that these terms, in normal situations, it will be proportional, because it's just the center of mass. It will be proportional to the number of particles that you are putting. These terms, it will be proportional like this, and you can make this if you make this assumption that the sum of these particles, they have some symmetries, you can change from this summatory to an integral from just 1 degree of freedom, not for different particles, for just 1 degree of freedom, by just changing by using the change property. And you arrive to this equation, and it can be shown that this equation is equal to 0. Okay, so it seems that unless for some circumstances there are clear evidence that there is some ontological unification between Bohmian mechanics and classical mechanics. And now I will show you some results. They are some preliminary results, but I will show you some results. These other results are just, I put here some parabolic potential. This is a parabolic potential. I put a lot of particles, wave functions, randomly. These are single particle wave functions, and these are Bohmian trajectories, also selected randomly. And then I put in this problem a change interaction. It means that to move all these particles, I have to solve the Slater matrix, not the Slater determinant, but because it's bosons, just the permanent. And basically, to deal with this number of particles, I have to compute 15 factorial computations. So it's a very simple problem, but it's already a crazy problem. Yeah. But unless with some computer and with some time, you are able to get the results. And the results is basically, from this random selection of the Bohmian trajectories, I can compute the quantum center of mass at the initial time. And I assume that this quantum center of mass is equal to the classical center of mass of my particle, and also the initial velocity. From this initial velocity, I move the particle classically, and then I move all these particles according to this exchange interaction, blah, blah, blah. And I compute the center of mass of these Bohmian particles, and I compute the error. The error is just what I get from the center of mass of the equation by following just Newton's law, and what I get by just making the definition of the center of mass of these Bohmian particles. And what you see here is time. What you see here is the error, and what you see here is just the number of particles. And what you see is that when you increase the number of particles until 15, we are now results that we are able to arrive to 18 if you wait 1 week for the simulation. But okay, and basically the important point is that obviously the error is not 0. But it seems clearly that you are decreasing the error of your problem, unless for this particular scenario. We have another scenario that says, okay, let us try to see what happens if we have a parabolic well. This is a parabolic well. It's exactly the same scenario. It means that the potential is proportional to x squared. Yeah? X to the 4. And basically, you see more or less the same. The error is larger, somehow is larger when you have 15 particles. But you also see that when you increase the number of particles, this error tries to decrease to 0, being this the error. So what I am saying is that for when you have one particle, I just one wave packet, one particle, and I move and I compare. When I have two particles, I put two wave packets, two particles, and I compare. And I'm doing this for until 15 particles. So this result seems to corroborate what we expect, is that when you increase the number of particles, in a very natural way, quantum mechanics arrive to classical limit. Okay, let us discuss how the quantum non-locality disappears. And it's very simple. It's very obvious. Yeah, it says, okay, you know that Bohmian mechanics lives in a physical 3D space, but the many particle wave function that is also part of the Bohmian mechanics lives in the high configuration space. You see here, this is a wave function in the two-dimensional space, and you have one particle that lives in the physical space. Yeah, but what happens is more or less obvious. More or less, what I am saying is that for one particle, it's difficult to say that this is zero. But if you have a lot of particles, and you have to sum a lot of terms, somehow, unless you prepare carefully the systems to avoid cancellation, most of the time you have some cancellation in front of this term that most of the time it has the same sign for all the particles. So this term tries to become higher, and this term tries to randomize and just disappear. So the answer is quite simple, and as far as you make the quantum potential disappears, all the quantum effects disappears. Obviously, non-locally and whatever else, because everything in the Bohmian particles that is not apart from this classical potential is just in the quantum potential. So when the quantum potential disappears, all the quantum effect disappears. Let us discuss how the quantum randomness disappears also in this problem. Okay, I have one experiment. This is my apple, and I put this a lot of particles with different wave packets and with a large uncertainty in my problem. Okay, but I compute the center of mass of this system, and this is the center of mass, and it's quite close to the classical center of mass. Okay, I make randomly another selection of wave packet because I'm doing another experiment. I'm putting another apple in the same place. And I select randomly different trajectories, but basically, because these trajectories are randomly, but I have to make the average of these trajectories, basically, my center of mass is not exactly the same as before, but it changed very few. It changed very few. And if I make another experiment, if I make another experiment, the center of mass is a little different from the previous two, but it's almost around the classical center of mass. So what I am saying is that for all practical purposes, basically the wave packet of my center of mass is something very narrow. It's something very narrow, but this is just very simple. Yes, it's just making average of random numbers. You make an average of random numbers can be positive and negatives, and the average means more or less very straight. Okay, and now I will show you how the conditional wave function of this wave packet evolves. Yeah. Now, if I want to look at the conditional wave packet of this system, I can use this conditional wave packet the equation that I showed you before, and I have three equations to arrive to the classical limit, but I have also these 3 degrees of freedom. And in particular, I have shown before that the quantum potentials, the sum of the quantum potentials can be more or less equal to 0. This is exactly the same as saying it's not equal to 0. They don't have to be 0. They have to be much smaller than the classical part. But more or less, it's the same as saying that if in the Newton-Locke equation they disappears, it's the same as saying that in the wave equation it appears this term. It appears this minus the quantum potential. And if you solve this equation, in red what you get is the wave function, the typical Schrödinger equation. In blue is the Schrödinger equation, and in red you see a wave function for this center of mass. And what you see is that basically they try to not disperse, to not make greater the dispersion of the wave packet because of this term. Because of this term, this equation is nonlinear. It's completely nonlinear. The conditional wave function is nonlinear. So basically, we are somehow discovering a new phenomena that is between quantum mechanics, pure quantum mechanics, and classical mechanics. Or if you want, you can use the word decoherence to say what we are doing. And I think that's all. So the two methods that I explained, the coherence and the many-body problem makes quantum theories universal and unfalsifiable for all practical purposes. This is a very attractive feature for an engineering point of view, because it means that he will be able, with Bohmian mechanics, to arrive to everything. But to arrive to everything that you have in the laboratory. But from a fundamental point of view, obviously, this is a disgusting result, and we have shown that without avoiding the concept of decoherence, we have shown that the Boolean mechanics for a many-body system, just looking at the center of mass, seems a very natural way of explaining the classical limit in a very simple and elementary way. And that's all. Thank you very much.